I don't know the exact figures, but I'm very happy to announce Bruno Putzeys. We met Bruno about 4 years ago, and in the meantime, that's Peter, Ilko, Bruno and I, we set up a company, so we work together on a regular basis, and that's why I'm very pleased to have Bruno here. Bruno's got a wide experience in audio. He even built tube amplifiers. He's probably very known for his Class D amplifiers that he designed at Philips and now for Hypex in north of Holland. And well, again, we're very happy that he's going to tell us a little bit about measurements in audio. And since we had a DAC shootout, we decided, well, let's take some DACs and perform some measurements. We found 3 DACs. The winner of the contest, of course, one non-oversampling DAC and a DAC that, in Bruno's opinion, measures according, let me say, the rules. So, please, Bruno, go ahead.
Thank you. Is this thing on? Well, never mind.
Yes, it's on.
Okay, cool. Hang on. Just
There's no slideshow.
No, there isn't for lack of time. So yeah, some of you might have been wondering what this decidedly non-vacuum tube personality was doing here. Well, the answer is quite simple. It's all part of a scientific experiment, and I was trying to find out if it was possible as a designer of Class D amplifiers to infiltrate in a society of tube lovers, to bring in an audio precision, and actually to have people tolerate me using it. Cool. So today my talk will be chiefly about measurements which one typically performs on D2A converters. It's not just to see whether a D2A converter performs well, but also the kinds of performance aspects that you might actually be designing for in if you're building a DAC and you want it to be a very good one. I'm not sure which DAC we should start with. Actually, I think it would be cool to take yesterday's winner.
Okay.
And
the box.
Yes, the beautiful Greek crate.
Actually, it's a modified IKEA box. I learned it from the designers, and I think
that does fit the philosophy, doesn't it?
it does.
So very charming. So how do we get signal on this?
Here's your digital inputs.
Okay.
Here, the red one.
What is it?
Tulip.
So you will need. Where am I going?
Je hebt daar een tulp. Niet zo gedekt.
Gooi?
Gooi. Ja.
Katja. Dan moet ik ook nog
Iets terugkrijgen. Waar wil jij dat hebben?
op die manier.
Zijn deze langer? Nee, die zijn langer.
Ik heb er anders nog wel een hoor.
Oké. Neem deze van je over.
Dus dan. Anders pak je deze niet tussen.
Links en rechts maakt jou niet zoveel uit, hè?
Nee, ik denk niet. Ik heb ze allemaal.
Oh, één kanaal.
Ja, ik ga volop in de hand
Oké.
op één kanaal.
Oh, en kun je dit nog ergens aan je meetopstelling knopen en aarden?
Wel ergens aan de rechterkant. So.
Zou die bronvrij moeten zijn?
Yes, but apparently they said the output was quite hot, but I'm not seeing much. On the it says 12 volts, and then it's THC plus an amplitude.
10 volt.
Okay, that's cool. Ja, er komt 12 volt uit. Okay, so let's first begin with a with a very basic measurement to get a feel for this DAC. Actually, the first measurement, which is simply plotting THD plus N versus the signal level, is going to tell us more about the back end. In this case, the tube buffer that follows the DAC, and not so much about the DAC itself. For the DAC itself, we'll have to take a closer look. But just first start with a quick sweep. So what I've set up here is I will plot on the y-axis the THD plus noise amplitude in dBs referred to maximum scale. The reason for that is if I plot the THD plus N referred to the signal, I can actually show you that, but you'll get we can actually first do it this way. So set it to ratio. We get distortion here. There's one, and I can plot distortion versus amplitude. As I say, go. And see there we go, and you get a diagonal line. So that line in effect appears to confuse quite a lot of people, because the question then becomes: is this distortion, and why is distortion coming down as the signal level is going up? Well, actually, no. What we are measuring in a THD plus N measurement is the signal. Is whatever remains from the signal after we've removed the test tone. So here we are testing with 1 kilohertz, and if you remove only the 1 kilohertz, you're left with harmonic distortion, but also with noise, and up to this point, so up to about minus 20 dB, referred to full scale, this distortion plot is dominated by noise. We can actually check if it's if there's any hum component in there as well. We can do that quickly by just cutting anything below 400 Hertz. There's not a lot of hum there. It is definitely only noise. So this is the bandwidth setting. I set this to, well, nearly DC coupled. On the high side, I've plugged in a 20 kilohertz AES filter, and the reason for that is that most DACs do produce quite a lot of noise outside the audio bandwidth. We'll see a very obvious example with this 1-bit based design, and if we want to know what is actually relevant to the sound, we should basically not bother too much with noise outside the audio band. But with distortion outside the audio band, it's a bit more tricky. Okay, so we've just made this plot, and as you can see, it's not very informative because of this. So what we do is we just slant it back 45 degrees, and actually plot the absolute amplitude of the distortion product. It may make sense to try and visualize a distortion product if you like. 0% amplitude. I'll just plump this into reading. See what this says. That's distortion only. So the actual signal is gone. Is this me? No. Actually, no. Does this thing have a hold off? I don't use this scope very often. So that, as you can actually see, it's maybe I should. I'm not sure if this is going to be long enough. I can't really plot the. I can't really plot the original sine wave. But anyway, so what we are seeing here is anything that remains apart from the signal that we wanted, and that's why it looks so shocking. So anyway, I set it to amplitude. So we now know that the RMS amplitude of the unwanted signal is 156 millivolts. If we know, however, that the output signal is a full 12 volts, it started at 12 volts. It's now 1185. So the gain is not entirely constant. So I'll just plot it referred to A. No, that was not what I wanted. So that's 38 dBs, and then here I can also network connections. How is that possible? I don't have that. So I'm now plotting. I'm now making the same plot, except that the distortion is now referred to the maximum signal level, and then you can obviously see that until this point, I don't expect this much distortion. So as you can see, sorry, the two axes. So this is the input signal referred to full scale. So this is a full scale input signal, and this is 1/10 of the full scale signal, and so on. You could also calibrate this in volts, but when you're measuring a DAC, it's more interesting to refer it to the amplitude in the digital domain. And then here you can obviously see this is constant. This is only noise, and here we have distortion. So the next thing we can do is actually have a look at what does this distortion actually look like in the frequency domain. Let me just quickly save this test so we can reuse it later. Actually, it was saved already. And have a look at the distortion product of the DAC. And there are actually two signal levels we're actually interested in two signal levels. One is the high level signal, which tells us what the analog circuit is doing, and we'll also make a second THD reading with very small signals to see with very small signals to see if the DAC has any low level linearity problems. Given that this is basically a delta signal based design, I don't expect this, but we might see we might find some interesting things later. So I set this to -1. I've got good reasons for setting this thing to -1, and let's see why is it? It's not complaining. That. What we're hearing here is the distortion, and I will, of course, when you measure a DAC, you don't want to measure the A to D converter, which is inside the audio precision. The A to D converter in there is pretty decent, but it's not brilliant. So at low signal levels, it's okay because the noise will dominate. At high signal levels, you will actually want to get rid of most of the signal by notching it out, and this is what the THD % ratio is. So we'll be plotting a spectrum of this of these 1.2%, and I tell it to go to amplitude. So this was 11.85, and we'll just do a quick plot and see where it goes. So this dip here is actually where the notch filter is removing where the notch filter is removing the 1 kilohertz fundamental. So the 1 kilohertz fundamental is gone, and we'll only see the distortion that remains. So the distortion here is clearly dominated by second harmonics, and then all the rest of the harmonics drop off quite quite gently. So this is typically the behavior of a tube-based output stage, and the fact that there's harmonic drop off in a monotonic fashion, according to some people, is why it is not a problem acoustically, and that it is not a problem acoustically has been established yesterday.
And this is a 12 volts output, Bruno.
This is a 12 volts output.
Okay.
So we can redo this, for example, at minus 20 dB, and then see the what we should expect at lower signal levels. That is that the higher harmonics will drop off much quicker than the lower harmonics. And let's just see if this is indeed what we are seeing. And indeed, at minus 20. Certainly, when you're listening to classical music, this is that's program level. That this distortion is fairly acceptable. Although I must note that this is still referred to 12 volts, but the fundamental is now at minus 20. So this is still only something like 56 decibels of distance. We see hum, and we see a lot of apparently hum-related components. Quite a few things which we don't really like to hear.
That's a distortion you're listening to.
This is well, what we are hearing.
Distortion plus noise.
It's distortion plus noise. So distortion is still there. If we turn the signal down further to minus 60, when I do that, I can actually start plotting the fundamental as well. And actually, and as you can see, there's no distortion after removal of this fundamental. The only thing we're hearing is this. It's hum, but also apparently some digital processing noise. But what older multi-bit DACs were often plagued by linearity problems, and these would manifest themselves at low signal levels, where you would actually get a spray of non-harmonic components, which are related to the signal. I'm quietly hoping that the non-oversampling DAC is multi-bit, so that we can actually see some of that happening later on. So this DAC actually, so what we see with this DAC, we see a lot of noise, we see a lot of distortion, but we know that this distortion is not coming from the DAC. Otherwise, we would have seen some untoward effects here. Another interesting one is obviously just checking the frequency response. Let's quickly see what we said. We're no longer looking at for frequency response reading. I might actually ask for a level reading. And again, plotting at plus one of at minus one of a dB. Plotting the frequency response. Go. Frequency response is commendably flat. We'll just see what happens at the bottom end, but that looks good.
Pretty good.
So that's indeed very clean. Now for something more interesting, which is jitter. Jitter is a form of is a form of phase modulation, and the absolute amplitude of jitter artifacts is proportional to the frequency at which we do the test. For that reason, it's common to use a very high audio frequency to do a jitter test, and it's also quite common to choose as the test frequency 1/4 of the sample rate, so that it's smack in the middle of the audio band, but still a pretty high frequency. And what we ideally would want to see is noise floor, perhaps with hum components or whatever, but otherwise just a vertical line at the 11 kilohertz. So what are we seeing? Let me set it to repeat, which is not necessary. I'll just ask it to do a couple of averages. The averaging does not remove noise. The only thing it does is it flattens the noise reading, so we can see deeper into the noise floor. So what we're seeing here is the input signal, and then to the left and to the right of the input signal, a lot of more or less symmetrical pattern of modulation products. And usually when the modulation products are symmetrical compared to symmetrical with respect to the test tone, then you can be sure that it's going to be either amplitude or phase modulation. If it's asymmetrical, then it's going to be a combination of both. Let's quickly overlay a plot of the noise floor without any signal present, so that we know that we are indeed looking at jitter. So as you can see, anything that's added here is indeed a jitter artifact. Another jitter test that's quite popular is called the Miller test. What this does is it superimposes an 11.025 kilohertz large signal with a low level signal of 1 LSB, and the amplitudes are chosen such that the bit pattern changes from a lot of zeros to a lot of ones. And then we might see if actually the data itself is influencing the clock.
Just one quick question, Bruno. The 20 kilohertz, what is that?
That appears to be the second harmonic of the test tone.
Oh, okay. But the test tone was at 11, so
no, you're
22.
Yeah. Yeah, but the plot goes to 2205, so it's really smack at the end.
No, but the 20.
And you see what?
20K.
That one.
Yes. 20K one.
Yeah. That's not the second harmonic.
No.
9 kilo away.
No, that indeed I thought you were talking about that one.
No, I meant the second one. That one, yeah.
You can see that it should be a 24.
That's indeed not very clear what that should be. Also,
Because it's also in the noise floor.
it's in the noise floor, but
Oscillation.
when you look, but you see that the level changes with the input level. So apparently it's crosstalk from somewhere. What I
Mystery.
Yeah, for the time being, it's that would that's
a measurement artifact for the time.
it's not going to be a measurement artifact. You can be pretty sure about that. This is what comes out of the what comes out of the DAC. I'll quickly see if I can if I can find back this Miller test on my test CD. I can't use the audio precision foot to generate that signal, so I have to do it from a test CD, which I've just written. It's not on the test CD, so I'll have to forget about the Miller test for the time being.
Yeah, we consider the range accuracies from 20 kilo to 30 kilometers.
Another test which is very popular with D2A converters, but which again is relevant only to multi-bit DACs or to find truncation problems in a digital filter, for example, is called level linearity. What level linearity does is you start with a full-scale sine wave, and you measure with a bandpass filter you measure only the amplitude of that sine wave, and you decrease the amplitude of the test tone, and because you're using a bandpass filter, you can actually read the amplitude below the noise up to a certain point when even the bandpass filter can no longer filter the signal out from between the noise, and the ideal level linearity plot therefore is just a diagonal line which goes on and on and on, and in reality it will flatten out at some level. Let's just check what this DAC does. The AP is getting a bit confused about something. Let's see what that. I'm going to fix it at 997 and hope that it does it again. It works properly now. So apparently the audio precision is getting a bit upset about some of the noise products it's encountering. What can I do? Does it help to set this to auto range? Measuring with an audio precision is always a bit of a tricky business when it gets into setting problems. So that doesn't work either. It's so I'm afraid we'll have. At any rate, let's be serious about this. We are plotting at -60, -80, -100, -120 dB. It's quite clear that here the noise is taking over and nothing strange is happening here. If, for example, the last few quantum steps in the transfer of a DAC were not perfectly monotonic, you would actually see jumps all over the place. And again, I hope I will see some of those a bit later on. So this more or less concludes the measurements on this converter. The only thing we can learn from it is that certainly for a group listening test, this distortion and even jitter specs may not be awfully important. The question remains, of course, what happens if one does a listening test at home and one has a couple of DACs available for a couple of weeks, and this is of course we would not be measuring any of those things if there weren't any reason for it. We'll probably rewire.
Next DAC.
Yes, I'll rewire to this one.
Dus
So
hier is nog eens
ik krijg van jou.
wat digitaals. Dit is een
En dan
kinderuitgang. Dus je nog die witte kabel water voor is. Dus we gaan hem uitzetten. Jij bent voorzien?
ik denk het test frequentie respons.
Zit er nog over?
Wat? Hoe heet die? Zegt die non-oversampled, non-filtered? En dan moet ik hier. Right. This is a non-oversampling DAC. Its output level, as you can see, is much lower than the previous contender. and we'll start with a quick frequency response plot. Yes, this is definitely an oversampling DAC.
It's oversampling. Which
Apparently,
DAC is this?
Peter,
It's oversampling.
Dit is normaal overzet, dit is geen normaal overzet.
let's have... Ah, maar wacht even, Guido. Daar komen gewoon spijkers uit.
Maar hoe kan die amplitude dan recht zijn?
Dan moet je hier komen kijken, dan weet je het meteen.
Zijn flesmuziek?
Ah,
Dus er komen, ja, je kunt er niet op triggers af. Dus er komen gewoon spijkers uit.
maar is nog niet te veel geweest.
Nee, maar zelfs dan had hem wel kapot kunnen zijn, maar er zit dus midden in. Is er een andere non-oversampling DAC die iets representatief is voor het chemisch? We'll have to get ourselves a different non-oversampling DAC because most of the phenomena that come out of this converter are, well, most unusual. Dus je kunt hem even... So as you can see, I'm trying to get actually rewire this straight to the oscilloscope. Hang on a second. So you have a look at what we are seeing here. Wat afval gebleven is met... Ligt er, ik heb hier even gewoon... That's 20 kilohertz, that. 20 nee, dus dit is inderdaad nog, hij zegt wel een oversampling. This is a 20 kilohertz signal.
sine wave.
Yes, it's a sine wave apparently. Well, actually, well, now we're looking at.
It was a sine wave.
Now that we're actually looking at the scope picture, I'm just going to skip to a small aside about non-oversampling DACs. Quite a few of us have experimented with those, and seem to like them. And usually the prevailing theory concerning why non-oversampling DACs sound pleasing has to do with the impulse response of the filter. Nee, mag mij gewoon het beeld geven hoor, het camerabeeld.
Oh. Sorry.
This has to do with the impulse response of the filter. As you can see, I've recorded here a square wave on this CD, and the square wave consists of a number of plus 0.5 samples followed by a number of minus 0.5 samples. And indeed, when you use non-oversampling, you get an absolutely perfect square wave. But the question becomes, what does a square wave look like when it is, for example, time shifted by half a sample? Because sampling theory allows us to do that, to shift the allows us to shift the waveform to by, for example, one half of a sample. And what does it look like then? Well, something like this. I might zoom into this for a second. This is the very same square wave, just half a sample later. And as you can see, the so-called fantastic impulse response of the non-oversampling DAC is no longer. because the beautiful flat-topped square wave exists only by virtue of a very artificial signal which happens to be sampled exactly synchronously with the original test signal, with the square wave. If it is not sampled exactly synchronously with the original square wave, you get this. Or suppose that we shift it with a quarter sample. That's what you get if you shifted it with a quarter sample. In other words, the simple fact that in a sampling system we still need to have a time precision of better than one sample means that we can sample a low pass filtered signal at times which are not necessarily coincident with the zero crossings of the ripple of the sampling of the low pass filter used in sampling. What if we take a square wave of which the frequency is not a submultiple of the sampling frequency? Well, it looks a bit like this.
What frequency we have now? 1 kilohertz?
It's not exactly 1 kilohertz. It's 800 and something. I just made sure that it was not an exact submultiple of 44.1. So this is what comes out of there. Okay, if we now quickly move to a bog standard oversampling converter like the one which is actually in this CD drive. It's not a particularly brilliant converter, but it is in a way good enough to it's good enough for the purpose of this demonstration. So I'll just plug round to here and go back to the square wave of track 9. Trigger. I don't know who's triggering an oscilloscopes. Right. So this is the kind of square wave that we know from an oversampling DAC, and this square wave is simply the mathematical direct result from the anti-aliasing low-pass filtering. And if you do that with linear phase, you get this sort of picture. And this is the same square wave, the one with long rows of equal samples. If we now take the second picture, which is the same square wave shifted by half a sample, we get this. Why has it suddenly changed amplitude? God knows. This is exactly the same. This is exactly the same picture, isn't it? So apparently, the use of low-pass filtering before sampling and after sampling allows you to reconstruct a signal with correct timing, irrespective of the relative timing between that signal and the sampling clock. So again, now the waveform with the quarter sample shift. Again, we get this. Now, I'm sort of suggesting that these waveforms are identical. They are not identical. Virtually all upsampling filters and virtually all decimation filters in the A to D D to H chain are based on a few assumptions, on a few simplifications, and they are not perfect low-pass filters, and they are not even perfectly anti-aliasing filters. What I mean by that is that if the converter is sampling at 44.1 kilohertz, we should not be seeing any harmonics above 22 or 50. But these filters cut off at 20 kilohertz, start rolling off at 20 kilohertz, but achieve zero only by 24.1 kilohertz, and the result is that there is still. So we are now looking at the square wave where this frequency is not exactly coincident with the sampling rate. you'll see that some of the harmonics of this square wave are still being allowed to alias, and they are all in a very narrow band between between 20 kilohertz and 24.1 kilohertz. This square wave was generated with an ideal low-pass filter, that is, with one which cuts off at 22,050 and immediately drops off to minus infinity. I.e., I've constructed this square wave with a bunch of sine waves. A normal analog to digital converter will have, I'll just zoom into this for a sec, a normal analog to digital converter will have some further attenuation, about 6 dBs. So when you feed a square wave into an analog to digital converter and then back to a digital to analog converter, you get this, and it's still not perfectly still. The point I'm trying to make is if either on the recording side or on the reproducing side someone would use a filter which lets no signal through, which passes no signal above 20 kilohertz, we should in fact not be seeing any of these wobbles. So well, I've applied just such a kind of filter to this signal. The filter ran flat to 20 kilohertz and then dropped off immediately to a very low level, and this is what you get then. It's perfectly still square wave, and this square wave is not sampled synchronously to the sampling rate. So this means that the timing precision of the zero crossings of a correctly implemented A to D, D to A chain is infinitely higher than just the sampling period. The sampling period is about 20 microseconds. A 16-bit system is capable of reproducing zero crossings at 90 nanosecond precision, and this is more or less what we are seeing here. So this is actually why I absolutely wanted to have a non-oversampling converter in this test. Was in order to show you that non-oversampling has nothing to do with the impulse response of the system. It is quite clear that the impulse response of a non-oversampling system is quite a bit worse than that of an oversampled system. Of course, then the next question is, why do they sound so bloody good? The answer lies actually in the type of conversion that's being used in all these devices, which is non-oversampling converters are always built with multi-bit chips, and these chips have all sorts of have settling time problems, glitch problems, which means that if the code changes from a 1 followed by a lot of zeros to a code of 0 followed by a lot of 1s, you get a certain amount of glitch energy, and this glitch energy is a certain time integral, which you take. So you have when you have this. Let's see. I might take the drawers. If you have, for example, a step between a code like
Another light, not so large.
Yeah, I'm not sure.
Or maybe just that curtain there.
Okay. Is that so? What I've just drawn just two random codes which are different, but by just the LSB. And what this means in a ladder DAC is that there's only one switch which will change state, and so you get pretty much a perfect step out of that. Suppose you change from this code to this code. Then you have 6 switches which are going to change state, and in the very worst case you would first have this this one becoming 1, followed by all these becoming 0. And what you get then is this kind of effect. And this is what they call the glitch energy. So the energy, the error between what we would have wanted to see and what we're actually getting.
And is this a function of this, the individual bits not switching at the same time?
Yes, exactly. And so given given a particular chip, a particular chip will always be generating at one particular code transition the same glitch energy, and so between every code transition you get a different impulse, but it's always, but for that particular DAC and for that particular combination of codes you will get the same glitch impulse. Now, if you reduce the sampling rate from say 352 kHz to 44.1, the number of glitches that you're going to see is much reduced. It's reduced by a factor of 8, which means that effectively you're going to see less distortion products inside the audio band by reducing the sampling rate. And this is the reason why non-oversampling DACs sound good. It has nothing to do with the impulse response. Also, that means that if you're designing, for example, a 1-bit DAC, which is sampling at a very high frequency, using that in a non-oversampled configuration will not yield any improvement, and worse, it's definitely going to sound worse than the same DAC with an oversampling filter. So it very much depends on the converter technology that you're using.
There's also the lack of a digital filter that doesn't induce jitter.
Yeah, that's correct. Quite typically, when you build a DAC with an upsampling filter, you'll just wire the upsampling filter straight into the DAC. The upsampling filter will deliver the bit clock, will deliver the word clock, or the sample clock, and a digital filter is pretty huge amount of calculation that this thing is doing, and the signals that come out of that are not very clean. Simply removing the upsampling filter from the DAC will allow the much cleaner clocks from the digital receiver to go straight into the DAC. So if you insert a reclocking circuit, just a bunch of latches below between the upsampling filter and the DAC, much of this of the mysterious difference between oversampling and non-oversampling will be removed, and the rest is due to this effect.
Can we measure the jitter performance?
Yes, we'll just quickly run the whole smash again. Let's see, where did this go? Where did this come from? Okay, can I get the computer screen back? Excellent. Then we might. Okay. So we were doing frequency response when we sort of were surprised by the lack of high frequency drop off. That's something for the mathematically inclined Guido and myself to figure out what on earth is going on here, because normally you would expect some droop on this on this end.
Can we measure beyond 20k?
Yes.
25.
Oh, but hang on. We are probably the problem is this thing is measuring RMS amplitude, and it's measuring the staircase as well. So I have to kill the staircase. So I'll pull in the AES17 filter, and ask amplitude here, and shock horror, we have a suddenly greatly reduced. Okay, that's good. So, and here I'll ask amplitude. So what actually happened was that we were actually measuring the RMS amplitude of this whole square wave, and not just of the 20 kilohertz component. So we were measuring both the 20 kilohertz component and its alias at 24.1, and these together summed up to the same level as a 1 kilohertz signal. So no need to do maths tonight. We could just listen to the concept. So okay, then. Oh, that's exactly what we were expecting. Yes. Wat? Ja, dat kan ik nog Okay, so this is so this is the frequency response of a typical non-oversampling DAC. It droops because the impulse response is a square wave, of which the frequency response is a sine x over x function. Okay, level linearity. That was actually that was a cool one. This is a What kind of DAC chip are you using in this? Where's Peter? What kind of a D2A converter chip is being used there? Okay, that's so this should be pretty cool then. So yeah, so we're probably not going to see anything shocking, as much as though I was hoping. If only I know what's going on here. I'm not getting any picture here. DJAM track, analyzer,
Is it that your reference voltage is only 330 micro?
Exactly. So it seems I've not lost my signal. I'm reading it from the wrong input.
There we go.
Good.
Thanks a lot. Good. Worse.
Good.
So apparently this particular chip does have some non-monotonicity problems, or well, it may be monotonous, but what we are seeing that at low levels, I must say this is below the 16-bit level. The step size is no longer constant, and when this happens near the zero crossing, which it almost invariably does, you will get this kind of deviation. So this is more or less what we want to see. Now, if this is going on well below 100 dB, I should say, don't worry. Open tests. THD versus amplitude. I presume that is going to be fairly decent as well. Don't forget to put this to BNC unbalanced. I have to. Wrong test. THD versus amplitude. So this DAC has an unweighted noise floor of minus 100 dB, and now we are seeing some interesting things happening. As you can see, distortion rises and falls and rises and falls. It's And now it starts to discuss. But actually, I don't. Actually, I worry much less about a monotonic rise like we saw on yesterday's winner, than a rise with all sorts of bumps, because every bump up and down corresponds to one extra harmonic in the spectrum. Okay. So let's see if we can count them. Open test distortion FFT outboard. So okay, and we'll start at -1 dB. So just we'll start just at -1. Actually, we could say 0 with a non-oversampling DAC. Then ask it to look at reading ratio and plot. So this is our distortion spectrum.
The fundamental is being notched again.
The fundamental is being notched. As you can see here, it's quite obvious that it's being notched. Again, distortion is a bit higher than expected. And it would seem to me, if we, knowing the DAC chip that's inside, that this is a settling time problem in the I2P converter. What we are seeing here, the DAC chip itself is capable of much better than this.
They actually 8844
So we go to -60. We'll no longer notch. And this is very typical for a multi-bit converter. That even at a relatively low level of -60 dB, there are quite a lot of harmonics there, and the harmonics are not just low harmonics; they are high harmonics, and this again has to do with the transfer function of the DAC, which is not a perfect staircase. Lastly, we can quickly.
Can we hear the signal of distortion?
Let's see if that's possible. Distortion FFT outboard, donk. So we are now at 30 dB. It's not clear as to what this is.
Headphone speaker, what do we have to change?
Yeah, but it says reading. That's the point. It says. En waar staat? Want er staat die THD percent ratio THD.
Ik heb niet 60 zitten.
Ja,
Ja, maar dat is hier, hè? Dat ik dat gedaan heb. So this is what we. But the notch is at 10k for some reason, and maybe I should set it to degen track. That's not what we would call a clean signal. Jitter FFT, XLR, BNC unbalanced. Okay. Jitter is pretty clean. Jitter is by all means very clean. Let's set this to 8 averages. Jitter is commendably clean. What we are seeing here is a few spikes. Usually, these two are jitter components. I'm not sure about this one. I'll just append a reading without signal to see which of the signals remain. I think that the 16 kilohertz is going to be an alias of this. So yeah, what we're seeing is some rubbish actually aliasing in the A to D converter of the older precision. No, we don't. So I presume because it's such a it's really very beautiful 16.0 hertz. So, but this in any case is not a jitter artifact. These two are because they're symmetrical. And what you would normally do if you want to know what's going on is you measure the frequency difference between the center frequency. We'd actually might have to zoom in, but and for example, such a component, it tells me that that there is a 2.45 kilohertz difference between. Is there any clock inside a normal converter that does 2.45 kilohertz?
I don't know what clocks you put in.
It's not the frame. It's not the frame rate, is it?
No clocks at all.
No clocks at all. Well, then your non-existent clocks are pretty clean. Let me put it this way. I mean we have little to worry about with this performance. Who's making all that noise? No, it's not the scope. Someone's making it.
There's an MP3 recorder playing.
Okay.
Could it be the actual beamer? Because it's also a 16 kilohertz as often comes up as a.
Yes, but this thing is one of these DLP projectors, and it's not scanning like a real CRT, and frequencies are very different. So let's not worry about this. The jitter performance of this DAC is pretty good. Period. I think we've had them. We've had them all. We can do a quick THD versus frequency, but that's not going to teach us a lot. Yeah. So we'll just quickly see if we can see any frequency dependence on the distortion, because that can also tell us where to look for. Well, I think it's pretty clear that we are seeing this. What we are seeing here is a slew rate related problem. Although at low frequencies the slew rate related problem should be much less because the steps are smaller. So I think the designer of this DAC will have to figure out a few more details. We'll just quickly plug in the last DAC in our lineup. THD versus frequency. Let's look at THD versus THD versus amplitude. Outboard.
This is the new deck, is it?
Sorry?
This is the third deck?
This is the third. We're now going to look at the at the third DAC. THD percent. Okay, and this is then. THD plus. Okay. So here we'll also do a THD versus amplitude sweep. This DAC apparently has a signal to noise ratio of 112 decibel. Scope again because it was not.
What DAC is it?
That's the thing that I built something like 4 years ago, 4 or 5 years ago.
It was in the shootout last night as well.
It was in the shootout and it was eliminated by Guido.
Why?
Why?
By the audience.
Well, I don't know. The thing is actually when we did a private shootout together some time ago, the difference was not as big as it was yesterday.
They were.
So there was like, well, okay, 2 good DACs, period. But on the other hand, usually I use this DAC as a clock master, and now I had to quickly rebuild it as a clock slave, because apparently the regulations stipulated that I was not to have to have a 2-box CD player. I offered to tape the 2 boxes together, but apparently that wouldn't do. So anyhow, so what we're seeing is that distortion doesn't really come out of the noise until at full scale. So if you want to stand a chance of seeing any distortion, you'll have to do so with a full scale signal, which will just do distortion FFT. So set this to.
Can you say something about the topology of this DAC?
It's a 1-bit design. Let's see if I can make this obvious somehow. Why is it not showing? Just trying to get it to get it on the scope. Oops, wrong button. Right. It's a 1-bit running at 64 times sampling frequency, which in this case is 2.8 megahertz. And what that does is it has a very low noise in the audio band, and right after the audio band it goes up like a brick wall. This is what you're seeing here. This is the wideband signal. If we filter this signal just down to 20 kilohertz, all the rubbish is gone, and you just get a clean low noise sine wave. We've just seen the measurement. It's 112 dB. But if we actually measure over a wider bandwidth, you'll quickly see that the signal to noise ratio will worsen. It doesn't seem to matter very much. It's the same principle that Super Audio CD is based upon. If you take a Super Audio CD player and you play on a test disc a test tone, get the same sort of thing. Right. So Oh, this was at minus at minus 60 the BFS, so it wasn't that bad. So it's bound to look quite a lot better now. It looks better, luckily. So reading amplitude plot. Right. So the 1 kilohertz is notched out. There's a second harmonic at just over minus 130. There's another one just a bit better than minus 120. That's the distortion at 1 kilohertz. We only have these two harmonics, so it actually makes sense to type 6 kilohertz in this. So we can actually have the second harmonic at 12 and the third harmonic at 18, and then we'll see some more distortion. Actually, no.
At full scale now?
This is minus 1 dBFS. So, okay. So if we then go to minus minus 60, I'm just again going to say. And where's it? A here. And again put it at 1K.
Your power supply is good too.
Yeah, absolutely.
I think so. Yeah.
Oh, something.
Minus one.
This is unnotched, yeah.
It's good. It's good.
So no harmonics. So this is basically behaving like a normal a normal linear circuit, which means that the distortion only appears at high signal levels, not at low signal levels. And actually, that's more important than the absolute magnitude of the distortion itself. We can have a quick look at jitter. Actually, the plot is there already. We can average a couple of them.
The jitter.
Yeah. So, and we'll run a second one with the test tone turned off. So we can actually see, because this noise floor will be the noise floor of the APs. So I don't know I couldn't exactly say what these two are. I suspect that they are from the audio precision itself, but it's not clear. They are not symmetrical with respect to the test tone, so by any means it's quite clear that it's not a modulation product or a jitter product. So that looks quite good. THD versus frequency is well, how should I say? It's something of a formality.
And at what level is this?
This is full scale because we couldn't see, there was at the distortion versus level plot. You saw that
Low scale.
that there was nothing there except at full power. So you had to turn
At
it.
least the distortion was within the noise floor.
Yeah, it was within the noise, and with the FFT we could actually see what it was. And indeed, the noise floor being at minus 112 and the two harmonics being better than minus 120, we're not going to find them. So yeah. A small rise at high frequencies, a small rise at the second harmonic. Again, the filter used in the audio precision cuts off sharply at 20 kilohertz. Which means that above 10 kilohertz there are no more harmonics to be measured. So the second harmonic goes off the scale here. This means that in a THD versus frequency plot, if the filter in the audio precision is very sharp, you can actually just count the harmonics. Each time it steps down. So that's about it. Let's say, are there any questions?
And you got the frequency response to that?
Oh yes, cool. It's probably, in terms of frequency response, this converter is probably going to be the worst. Hang on, I have to. Yeah, okay. It's probably going to be the worst of the pack.
So my question is, Bruno,
Yeah.
your measurements were obviously almost perfect. How come it didn't win the shootout?
Quite simply because you can't win a quick shootout against tube-based gear. It's
Against tube-based gear?
Yes, exactly. The thing is as much as tubophiles might abhor the idea of even admitting it, tubes can be and often are euphonic. So if I'm playing by the rules of absolute accuracy, and someone else is playing by the rules of this has to sound as beautiful as it possibly can, well, it's obviously the second one is going to win. And I find this not only with converters, I find this with amplifiers. If you design an amplifier, even if you do it by ear, but if your goal is absolute, just precision, neutrality, everything you want. If you do a shootout, this amplifier is going to be the most bland in the whole pack. It's always so. This is
A bit like Korean cars.
sorry.
A bit like Korean cars.
Well, maybe yes, maybe. But I do hope that Ferraris have less flaws than Korean cars.
But are you saying, in conversion, are you saying that on a long-term test, a more technically proficient amp may end up being preferred?
Yeah. Yes, because this converter has been in a lot of people's hands, and they always come back saying that oh, when I first turned it on, I didn't get what was the point. I didn't get the point of it, and then after a while switching back and forth, they say, but this thing delivers the goods, but it doesn't do anything more. And
Well, I have a remark to shoot out. People are not voting consistently. At some of the shootouts, I'm very convinced that in the example with Allen's was the winner. But in this, and it was a rather close race. But in most cases, people seem to like a little more power up front and the sound online with speakers.
well, it's quite possible. But then
Yes,
again,
but people are not voting consistent with that view, and I think that at least in two of the cases, the losers was the winner.
well, it will certainly
One
be.
was Allen's.
I'll simplify.
Listeners, what do you want to see?
I'll simplify the discussion. The major goal of the shootout,
Is to have fun,
at least Emil and I decided, is to create an environment where we can stimulate people to bring most weird constructions and listen to some fun music. And of
It's not
course,
meant to be scientific.
of course.
So actually, it would have been surprising to see how this would come out first.
Yeah. Well, no, I'm serious. We like to compare things and we like to listen to them, but there's no competition element at all, I should say. I mean, everyone does their best and makes their thing according to their own knowledge or preferences and whatever, and we just put them together.
Well, I'll go out on a limb though, that any of the DACs that ended as the last 4 or 8 were all good sounding DACs.
That's
Because I'm sure that in a shootout, if one sounds like crap, it'll get voted out. If it hurts your ears. you know?
I guess so.
Yeah.
But it doesn't mean that the one that won, if you were to listen to 2 of them for a month, you're going to say that's better than the other one.
Yeah.
Yeah.
So I mean, it's also
The whole thing
huge
is
concentration.
just
Of course.
it was just a game and have fun with the hobby that we have.
Exactly.
Yeah. It's been my experience. There's no justice in it. It's been
Yeah.
my own.
But then there isn't supposed to be, I think.
Exactly.
It's been my experience that people basically, like when they walk into a place, they're looking somewhere to hang their hat, you know, and they're listening for something to latch onto. And
Okay, if there's some more
I had
technical
a fellow,
questions.
a fellow that called me from America. He said, you must make perfect amplifiers. I said, sir, I don't make perfect amplifiers. I cannot live with a perfect wife either.
Okay.
this is the bloody limit.
How much better with your measurements.
Okay, cool, I made someone happy. I hope I've made everybody happy.
So another question then? Is there anything missing from the this measurement, this system that you would actually like? Is there any facility that it doesn't have that you want? Because I'm mighty impressed.
It doesn't make coffee.
Doesn't make
Well, for the time, yeah, the price is.
Price tag.
What do they go for? 20,000 or something?
Yeah, that's 25 to 30k. I got this one secondhand, luckily.
I once saw on eBay one go, and I missed it. It went for something like 4,000 or 5,000 euros. Yeah, somebody was sleeping that day.
This one was sold via the Hans.nl at 5k.
Oh, really?
Yeah.
There's a light version of the with your precision
Yeah.
test device.